to you. So I'm Takemasa Miyoshi. So I'm going to talk about the data assimilation. So this lecture is supposed to be about the weather and climate simulations. And I have been working on the weather prediction problem, but my expertise is data assimilation. So I focus mostly on data assimilation with some introduction about the climate modeling. Okay, so let me first introduce myself. So I had an experience in the government office. It's not really a government lab because this is a Japanese meteorological agency. That's a government office, not a lab. And I did the general administration. So it's completely different from science. And I learned how the Japanese government is working, the system in the government. I spent for 2 years right after I graduated from the undergrad bachelor's degree from Kyoto University. And then I moved to more technical part on numerical weather predictions. This NWP stands for Numerical Weather Prediction Division. So this is the time when I started the data assimilation as a government. So at the government office for developing the numerical weather prediction system. So now the numerical weather prediction system is a fundamental method for weather prediction. So this is basically how we create the weather prediction that we see every day. And then I had a chance to study at the University of Maryland. Again, I finished only the bachelor's degree here, so I didn't have any graduate degree. So I had a chance to study at the University of Maryland for graduate school. This is part of the government training program, so only for the Japanese government employee. And I was a student there, and I had 2 years. That was very strict because this is a training program, part of the training program, the government. And I was supposed to finish the master's degree, but I also finished the PhD. So this was record. Fastest record, I think, at the University of Maryland. And then I went back to the Japan Meteorological Agency at the numerical weather prediction. And what I studied here in my PhD was about the ensemble data assimilation method. That was not in operational use at that time. And so I started developing it for the operational system. And 3.5 years were not long enough, but the people that my colleagues there spent like 10 years after that, and finally this system that I started developing there is now in use, operational use. So every day we see the forecast from the weather service of Japan. So I'm very happy to see that. And then I quit the JMA and moved to the University of Maryland as a faculty. So I was an assistant professor there. So I had an experience in the government office and a graduate student and a faculty at the same university, the same department of meteorology at that time, but they changed the name to be the Department of Atmospheric and Oceanic Science. And then about 6.5 years ago, I moved here, Kobe, and I have been working with the K computer. So I'm going to talk mostly about what we did with the K computer. That's actually the cutting edge of this type of research. So now I have many responsibilities. 3 of them are related to RIKEN. So RIKEN is one of the biggest research institute, like a government lab in Japan. And there are different programs, but my main job is the team leader of data assimilation research team here at RIKEN Center for Computational Science. And I'm also a visiting professor at the University of Maryland and Kyoto University. I'm teaching the class. So yesterday I was teaching in Kyoto University the data assimilation in the math department. But my background is meteorology. So I'm not a math professor, but I'm teaching in the math department. You will see why. Because data assimilation is more like an applied math. Okay, so you know that this is the flagship institute in Japan for computational science, and we have this supercomputer. And 6.5 years ago, I was thinking what we can do with this computer. And now it's retiring, as you know, and then we will have the next one that's basically 100 times more powerful than the current K computer. The K computer is like 8 years old, and 1 year for computer age may be equivalent to like 10 years of human age. So 8 years old is somewhat equivalent to 80 years old, so it's time to retire. So my group on data assimilation research, we have about 15 scientists, and it's kind of stable, so people come and go occasionally, and we are about 15 all the time. So mostly we study about the weather prediction problem. So these are the two pictures, one from the computer simulation and the other from the real satellite. Can you tell which is which? So this is a good quiz to test your eyes. Okay. Okay. So let's say, so which is the simulation? Raise your hand if you think A is a simulation. Okay, I can count 1, 2, 3, 4, 5. Okay. Raise your hand if you think B is the simulation. Okay. More, many more. Okay, so it's very hard to tell. That was the point, but it seems that you have very good eyes or very bad eyes. I don't know the answer yet. Okay, let's see. So I have a movie, and you will see which is real and which is not real. So the first thing to notice is this color change. Because of the infrared sensor, we see the temperature from the surface. And the simulation doesn't have that effect in this case. So we can simulate, but we didn't. So that's why, well, but this is not fair because we didn't see that in the previous. So, okay, so at the beginning of this simulation, we see more clear difference. Okay, so this is near the beginning of the simulation. This simulation starts from the low resolution initial conditions because there's nothing like high resolution clouds analyzed in the computer. So we can observe the very fine structures of the clouds from the satellite. It depends on the satellite sensor. So if we can see more detailed picture with a nice imagery sensor, then we can see the details of these clouds. And this is a previous generation of, or even older one, geostationary infrared sensor. So it has like 4 kilometers mesh here. And this simulation is 3.5 kilometer mesh. It's very similar, but we don't have the initial condition, good initial condition. So that's why at the beginning, the clouds are really vague because the resolution is like 60 kilometers. It's like 10 times coarser than the model resolution. And then we have a strong spin up because the model is 3.5 kilometer mesh, but the data is only like 50 kilometers mesh. Then the model tried to generate the small scales, and that there is a jump from the initial state that we give. That's why at the beginning we have some strange jump. You can see this, yeah? So this is the typical problem when we initiate the model. And then, well, it's harder to see the differences because this has a 3.5 kilometer physics inside, so we can see the detailed structure of the clouds. Okay, so the answer was, this was the simulation. And it turned out that most of you in general have very good eyes, even though I assume that you are not an expert in the weather prediction. The expert may not see, well, clearly what's the difference. Well, okay, so first we would like to know how we can make this type of simulation, the high resolution simulation. So in general, we have a model with a discretization. So it's a sphere, And this is one method of this discretization. There are many, many different ways of discretizing the spherical coordinates. But now we have a sphere with icosahedron. So there are 20 faces here. And then we divide each triangle into 4. Just divide. And then it's a second generation of this. And then it's the third and fourth and fifth and more. Then we can make even higher resolution. So this is an example of the Earth topography with different resolution discretization. So you see hexagons, because each point here, only this has only 5 pentagon, but this is hexagon. So most of the points will become hexagon. Only these 12 points, those are the unique points from the beginning, have pentagons. So if you look carefully, some should be pentagon, only 12 pentagons, and all the others should be hexagon. So that's why we see a lot of hexagons. So we can make the higher resolution by dividing each triangle like that. And this is Japan. And this is 60 kilometers. So this is about the resolution that we make, the data assimilation. I will talk about the data assimilation later. And this is the 30 kilometers. Now we see a good shape here. And this is the West Coast and Rockies of the United States. And 15, this is about the resolution that we see now at the top weather prediction centers. Now run the global weather prediction at this resolution, like the European Center for medium range weather forecast, ECMWF. They are known as the best performing weather prediction in a global model. So this is the resolution that we have now, and the higher resolution is higher than that. So this is something that we explore beyond what we can do with the operational weather prediction. And 3.5. So this is the resolution that I showed at the beginning. Yeah, and this was done actually in 2003 with the Earth Simulator supercomputer. That's a 40 teraflops supercomputer, and that's only like a single node right now. So now we have much more computations power, so we can do more than this. Okay, so how do we compute the weather? So we define the variables, the weather variables basically, the winds, temperature, humidity, clouds, and pressure. These are the basic variables. And then we know, so this is a human knowledge. So we know the physics, and we know the physical law to control these variables, how these variables evolve. So we have a model based on the dynamics and physics. So it's basically a Navier-Stokes equations and with the phase change of water. And then we can predict the future. So we give the initial conditions. We need to provide necessary boundary conditions like a sea surface temperature or the ground conditions or the solar, the insolation, and those. And then we can compute how to warm up the atmosphere, or we had a very warm day today. We can compute that and make the forecast. So this is the basics of the weather simulation. And now we can do this 870 meter mesh. So what I showed at the beginning was 3.5 kilometers. So half of that is 1.7, and half of that is 870 meters. So 2 more divisions of the grids will make this. And this is still the highest resolution simulation in the world still. Although this was published in already 6 years ago, this was done by the K computer. My colleagues did it. I didn't do that with this K computer. So this is really amazing because we can see the detailed structure of the clouds everywhere in the world at 870 meter mesh. So this is really a huge computation, and we get really a big data, and the visualization took a lot of time. So we spend like 24 hours of computation to make 24-hour integration. So this is never be forecast because we can go at the same time with the real world. And then we get lots of data to make this nice three-dimensional movie plot. It took us like 3 months of the visualization, just processing the data to visualize. So it took 3 months. So this is really amazing simulation. So this is something we do with the computer. The data assimilation is all about merging the data in the computer with the real world observation data. So this is actually the real observations of a convective cloud. So every 30 seconds we get the image, the dense three-dimensional image. So this makes the movie of this type of convection. So this is really amazing. So this was done by this new type of radar that's known as the phase array weather radar. And this is not like the parabolic antenna. And we can observe 100 vertical levels simultaneously so that we get 100 times of more data than the previous, the usual parabolic antenna radar. So this is also a source of big data. So the question for me as a data assimilation scientist is what we can do or how we can combine these two amazing things. One is the very high resolution simulation. So this is purely virtual computation. And this is a real. So we observe only partially, but a very detailed structure of the real world. So we would like to combine these two. That's the idea. So data assimilation is all about this plus sign. And what we thought is that we can synchronize the state observed like this and create this exact state in the model. Then we can predict. Now we have a sudden rain that we cannot predict, but with this sensor and this high resolution model, we could predict the rain, although we cannot remove the heavy rain. Maybe the ultimate goal will be to control the rain so that we can avoid having it anyway. But at this moment, we are more humble and we try to predict and try to escape or prepare. So this happened in Kobe in 2008, and 5 people unfortunately died. Only 5 minutes difference, 10 minutes difference. So 10 minutes before, 10 minutes later, we get this people playing here. Unfortunately, 5 people died. So that was a strong motivation for us to develop this system. Okay, so the idea again was to combine the big data from the real world observations and the big data from the simulation using this powerful supercomputer. So this can be generalized to different problems, but for now we focus on that convective weather system. So we had a fortunate combination of this K computer and this phase array radar. So they developed this in 2012, and we had this K computer in 2011 or 12. So we proposed this idea for research in 6 years ago. So it was almost the time when they started using these things. So this was very, very fortunate combination of these technologies. And then we developed this system. So it took us like 3 years to develop this workflow. So we get the data every 30 seconds. So what we try to do is to use all of the data every 30 seconds without any loss to make the prediction for the next 30 minutes. That's what we could do with this computer, even with the K computer. So we get the data every 30 seconds. So after 30 seconds, we get the next data. That means that we need to finish our computations within the 30-second period. So we need to process the data first within 10 seconds. and we pass the data from the radar site to the supercomputer. And this also required some development of the communication system. And then we run the data assimilation to combine the data with the model, and the model can produce the forecast. So this is very fast. We tested this system for a past case. So several past cases, but this is one of the cases. So at 8 a.m., I saw this, and 5 minutes later, 10 minutes later, so this red is very heavy rain. So only 10 minutes, it changed quite rapidly. And then it kept developing like that, and this became like that. So this is Kobe, so you must be very familiar with the geography by now. So this is a Kobe Airport Island, where we are here at the southern tip of this port island. And this is Sannomiya, the main station. So I live somewhere close to Sannomiya station, and I bike every morning. So I looked at this image. Okay, so I have to say that I'm a PhD in meteorology. I was a professor teaching weather analysis. And I looked at the sky, and I thought that this is okay to bike. And it took me like 30 minutes. It usually takes 30 minutes from here to here, biking. So this was really bad, actually. But as you can see that 8:30, I arrived, and I was okay. So I felt something on my back, but I didn't look back, and that was fortunate. But if I knew that this rapid development of this convection, I would never biked that morning. So this was a critical event for me. That's why I chose this. As a PI, I had a right to choose what case to study. Okay, so this just shows the area. So this is Kobe Airport, and this is where we are. On top left is the observation. Top right is the simulation with the data assimilation that we developed this system. And the bottom left is a regular weather forecast without assimilating this data. Okay, so this is the forecast that we usually have. Just ignore this for the moment. Okay, so we start observing the rapid development of this convection here, the heavy rain. And we can generate that in the model by assimilating this. But without the data assimilation, we have nothing. So there's no predictability at all. That's why the rain comes suddenly. And that's why I biked that morning. So we can see that very detailed structure of these clouds. I don't have time to go over all the movies, but you can see the RIKEN channel, that's YouTube RIKEN channel, has several thousand of content. And it's ranked number 6, the number of views. So if you are kind enough to click and see this movie, this digit will move. Thank you very much for your cooperation. Okay, so this is the snapshot. Okay, so we see the observation like this, well produced in the model. Again, this is purely virtual, because this is in the model. And this is a real from the sensor. And if we run just a model without using this data, we cannot predict at all. We cannot generate this system at all. So this is the power of data assimilation. So how can we do that? So the general idea is to combine the simulation with the observations. Yeah? So conceptually, we would like to add some value in each of these. Okay, so this is a data-driven, the real, representing the real world, but this is again the cyber world, or just the virtual computations. But this is process-driven, so we can simulate what will happen based on our understanding of the nature. So we have a physical law of all the Newton's law of those, and we can compute. So combining these two completely different approaches, the data assimilation can add something more than what either can do. Yeah. So this can be viewed as a problem of chaos synchronization. This is a concept in the applied math or the control theory. We have a nature system, but we cannot know the nature perfectly. And we have a model to simulate the nature based on our human understanding about the nature. And what we can get from the nature is just a partial information, not the perfect, but imperfect information. So the idea is to make this model synchronize with the nature. Yeah. So we can discuss the stability of the synchronization. If the synchronization is stable, then we can make the model be very close to the nature, and we can make the prediction. So this is what we do in the weather prediction. So the stability is, well, so the stability depends on the instability in the dynamics. So if the dynamics is more unstable, then the synchronization is more difficult. So it depends on the strength of the chaotic nature of this system. So it really depends on what we would like to predict here. Yeah. Depending on this instability, so this we cannot control because this is given by the nature. But we can control what we observe, for example. So if we have a strongly chaotic system, then we need to have more accurate and dense and frequent observations, like the case that I showed. Because the convective weather is highly chaotic and change very quickly. In 10 minutes, it changed very quickly. That's why we had to use every 30-second data. That's not the regular weather forecast. The regular weather forecast usually focus on the large-scale phenomena, like the low-pressure system and high-pressure system move like that, and the 2 or 3 days later, we have rain, something like that. That has a different strength of chaos. It's a longer scale, larger scale. That's why we don't need the every 30-second data. Every 30-second data doesn't really make sense for that. So what we need is a satellite observation for broad scale and the synoptic weather stations. Maybe we have the weather observatory maybe like every one in several hundred kilometers away each other, something like that. It's good enough. So it really depends what kind of observations are effective for this prediction. Yeah. So this is very essential point. And the data assimilation can provide the method to suggest what observation is effective. Okay. I will just go this theoretical part to explain what process we use in data assimilation, and then I will conclude my talk. Because this is time. So we can generalize the problem of data assimilation like this, because if you think this n as the time step, then this is a system that evolves in time. So if we give x1 to be like this number, then we can compute the x2, that's the next time step, and then we can compute again and again to make the future state like this. If we give a is 4, then we know that this is a chaotic system. That means that the time series like this, and time series started from this with small noise will lead to a completely different state like this. If we plot this, the blue time series and red time series at the beginning, it's almost overlap each other. But at some point, the blue and red are going apart. So we see slight dislocation of red and blue here, but it's completely different time series after that. So this is the nature of the chaos. So the question is how we can synchronize these two time series. So if we use this this blue value here, exact the same value here. This is an Excel sheet, by the way. So we can get exactly the same state. So it's not interesting at all. So assume that we can get only noisy observations. That's a partial transformation of the data, the information. Then we get some blue circles here that has noise from the blue curve. Then we apply one method of data assimilation known as the Kalman filter. We get this red time series. So the red time series is closer than the blue circle to the blue time series. Yeah, it's because we take advantage of both the data and also the process. So we have a state at n and n plus 1, so we need to know the process to do that. That's the simulation. And then we combine with the data. So we make the forecast and combine with the observation to make a better state. So that's the process of data assimilation. This is all about the errors. So we need to understand the errors. So to think about the errors, what we do is the probability theory. So we make the Bayesian estimation. So if we get the forecast at this value, then we have some range of uncertainties. And the same for the observations. And if we combine these two based on the Bayes, then we get the better state, better than either. Okay, so this is merging A and B. So if we assume the Gaussian function, we can compute like that. If we can assume A and B are both Gaussian, and this is Gaussian, we can compute that. And with a narrow and higher, okay, somewhere in between A and B. So this is what we do in numerical weather prediction. So we start from some estimate of the true state. The true state never known. And we make the forecast, yeah? And then if we keep forecasting, the forecast goes away. That's why the weather forecast gets less and less accurate. So we take the observation and combine these two based on the previous process. And then we can make the forecast. So we repeat this again and again. So this is known as the four-dimensional data assimilation, because if you consider here this analysis is a combination of this observation and forecast. This forecast came from this analysis, and this analysis contains this observation. So this forecast is available because we had this observation. Without this observation, the forecast goes somewhere there. So we got this because of this observation. So that means that we succeed the information in time, so that this analysis contains all the information from the past observations. So that's how we get the better forecast. Okay, that's how we combine the process and the data. Okay, so I think I need to finish my talk, although I have like tons of more slides. Okay, so I will just talk about this as a final slide. So this is not all, but what the data assimilation can do. Data assimilation can do it, maybe more than this, but this is something we have been doing so far. And first of all, we can make a better prediction. So that's why we use the data assimilation in numerical weather prediction. And for the better prediction, we get the state estimate, the better state of the initial and boundary conditions. And also we can estimate the model parameter. So we optimize the model parameter. We monitor the difference between the observation and the simulation so that we minimize the difference between these two. And we can integrate different types of the data. So that's maybe the most powerful application of data assimilation. So the highest, the citation paper. So the highest cited paper in all geoscience field, maybe about this product of data assimilation. Some of you might have heard of the NCEP-NCAR analysis. That's so they produced 40 years of record every 6 hours estimate of the atmospheric state. That initiated whole research on the climate processes or the dynamics of climate. So that's the time series of this state in the model. That's a very regular data, because we have gridded data, and every 6 hours. And we consider the satellite observations and the station data and everything all converged into this state. So that's how it's very useful data, and that's probably the most highest impact research so far. But now we can do more. For example, we can identify the model equations or model error bias correction and inverse problem solver and these. And I think I have to stop now. So thank you very much for your attention. And if you have any questions, I think I can spend like 1-2 minutes. Yeah.